Hello everyone. In a previous video, Signals and System Part 1, we covered these four topics. In this video, we will cover these remaining topic in the chapter, which is classification of systems and system modeling, basically deriving a mathematical equation that relate input to output. When we talk about system, we mean it's like a device that can take an input, process it, and give you an output. And this system could be electrical system, mechanical system, biological system, or financial system. In this course, we will focus on one input, give you one output. But in general, you can have systems that take more, 2-3 inputs and give you 1 or 2 outputs. So let's learn about the different type of system and how do we classify them. So the first classification is linear and non-linear system, time varying or time invariant system. Is it an instantaneous system or dynamic system? Causal, non-causal system, continuous or discrete system, analog and digital system, invertible and non-invertible system, and stable and unstable system. So we're going to go through each one of them in detail. When we talk about linear system, basically if you have a system here and you have one input, and let's call this input x1, then you get an output, and let's call it y1. Now if I have a different input x2 and I get a different output y2. Now what happened if I have an input that consists both input, a combination of both? So it's like x1 plus x2. So these two inputs appear at the same time and hit the system. If the output consists of y1 plus y2, then we say the system is linear. If I multiply this input by a could be 2. So basically now the input is twice x1 and the output is ay1, then the system is linear. So these are the two conditions for linearity. If I have an input and I amplify it, then the output will be the same for x1 amplified by the same amount. If the input consists of both x1 and x2 and the output consists of y1 and y2, then that's a linear system. So this is the mathematical condition for a linear system. If it doesn't meet this condition, then we call the system non-linear. Let's take an example to demonstrate this concept. And let's start with this example first. Is this system linear? So this basically is a system. It takes an input x1. It gives you the output, the square of the input. So that would be x1 squared. If I have another input x2, then the output will be x2 squared. Now what happens if I have both input hit the system, x1 plus x2, so that's the input. Then according to this system, it will just square the input. So that will be x1 plus x2 squared. If I express this in a different way, square it, x1 squared plus x2 squared plus 2x1 x2. Now this one does not equal a combination of these output. If I call this y1 and this y2, it does not equal y1 plus y2. It does not equal x1 squared plus x2 squared. So this system is not linear. And you can think of linearity in a different way. If the input is here and this is the output, if the equations that relate x to y a linear line, then that's a linear system. For this case, if I plot it, it's gonna look like this. So that's not a linear system. Now let's look at this example and see, is this system a linear system? So we're gonna start with the following. If I have an input x1 and I have an output, let's call it y1, or a second input x2 and an output y2, and a combination of both of them, x1 plus x2. If the output is y1 plus y2, then the system is linear. So let's take this scenario first, x1 and y1, and plug it in this equation that describes the system. So this will be dy1 dt plus 2y1 equal x1. X is the input, y is the output. Now let's apply this input. In this case, the output will be y2. So that will be dy2 dt plus 2y2 equal x2. Now what if I apply now this input and this output? So if I plug this in this equation, it's the derivative of the output. So that will be d. The output is y1 plus y2 dt plus 2. The output y is now y1 plus y2. The input x is now x1 plus x2. So now this is equation 1, and let's call this equation 2. Equation 1 for this single input, equation 2 for this single input. Equation 3, let's call this equation 3 for this a combination of inputs. Now if equation 1 plus equation 2 equal equation 3, then the system is linear. Basically, it meets this condition. So let's see. Well, this equation, equation 3, I can express it as the following. dy1 dt plus, so I'm opening this, dy2 dt plus 2y1 plus 2y2 equal x1 plus x2. Now, if I add these two equations, dy1 dt plus dy2 dt, that will be dy1 dt plus d2 plus 2y1 plus 2y2 equal x1 plus x2. Now, when I compare this equation 3 with this equation, which is equation 1 plus equation 2, they are the same. So the system is linear. And that's how we test linearity for a system. We just assume inputs and plug it in the equations that describe the system and see if it meets these conditions. Now, can we say different organ in the human body? It could be the hearing. Is it a linear system or non-linear system? Well, if I play a sound like a beep and I increase it by a factor of 2, you will hear it louder. But is this loudness going to be double? So let's say S1 is just a beep of 100 hertz. Now, if I increase the volume by 2S1, so I increase it twice, is my hearing perception gonna sound like the volume increased by a factor of 2? Maybe yes, but how about if I increase by a factor of 3? A factor of 5. Now, if I increase by a factor of 5, this won't sound as loud as this one 5 times, because there will be a feedback to the stapes inside the middle ear for the muscle to contract, and also inside the cochlea, the basilar membrane, to contract, because the brain is telling my hearing mechanism there is a loud sound may damage the hair cells, so the muscle starts contracting to minimize the vibration, and my perception of sound will not be 5 times this. If that is the actual volume of the sound and this is the perception of loudness, it goes like this. So it's almost like linear here, but then it's not linear. And the same thing for a human visual system. And in fact, many organs in our body, because of the feedback, is not a linear system. But for electrical, mechanical, many systems we use are linear system. And the advantage of linear system is the following, especially in signal processing. You can have a very complex input to the system. That could be just like this part, this curve, part of the input. Now, if I know how the system responds to a pulse like this, maybe the response something like this. So if I know how the system responds to this, now I can express this complex input as a linear sum of pulses. And because the system is linear, the output of the system will be the output due to this pulse plus the output due to this pulse plus the output due to this one, and you sum all these outputs, and that will be exactly the same as the output to this curve. And that's only because of linearity. And that's the advantage of linearity. So basically, I'm expressing these, if you call this x of t, I'm expressing it as a linear sum of pulses of different amplitude. The output will be the output for this one, which is this, plus the output for this pulse, which is this, plus the output for this pulse, which is this. And that's the advantage of system linearity. Okay, the next classification of a system is time-invariant system. That means, does the system respond to the same input the same way? If this input hit the system in the morning or in the afternoon or at night, the system doesn't change its behavior. If it doesn't change its behavior, then we call the system time-invariant system. So it doesn't behave differently at different time. If we think of human as a system, we are time variant. We behave for the same input different way at different time. You can come in the morning while my mood is good and give me bad news, and I will react a certain way, more calm maybe. Come while I'm stressed in the afternoon and give me the same news, same input, then you will see a different response. So human psychological or biological system is time variant. But for our system we build, like cars, airplanes, we want it to be time invariant, so it behaves same way at night, in the morning. Some systems we want it to change with time. Then we call this system time varying. So how do we test a system if it's time invariant or not? Well, if this is the input x of t that starts at t equals 0 and give you this output, and this is the system. Now, if I take the same system and take this input, but instead of hitting the system at t equals 0, now it's hitting the system at capital T. That could be 1 o'clock in the afternoon. And if the output of the system has exactly the same shape as this, but it's delayed, then the system is time invariant. If the output looks something different like this, then we say the system is time variant. So how do we test? Is this system time invariant or time varying system? Well, the test is simple. First, you take the system you want to test and excite it with an input and find the output, y of t. Now, I will delay this output y of t by any value of second, t second. Maybe I will delay it by 2-3 seconds. This is the output after the delay. Now, if I take the same input, x of t, and I delay it by the same capital T as here, so now this input exists maybe at 1 o'clock in the afternoon. And this input hit the system I am testing. So now the system I'm testing here, it shows the input maybe 12 noon. Now this system, if capital T is 1 hour, now this system is seeing the input at 1 different time. And if the output is this one, same exactly as this output, so if these two are the same, then we say the system is time invariant. If these two outputs are different, then system is time varying. So let's take an example. And first we're gonna take this example, A. So we take it to the system. So basically this system is just an amplifier. It amplifies the input by a factor of 3. So if this is the input, x of t, then the output will be just 3x of t. Then I take it to a delay, let's say tau. So then the output will be 3x of t minus tau. And tau could be 2 seconds, 3 seconds, 3 milliseconds. Now let's delay the input first, then hit the system with this delayed input. So I'm going to take the same input x of t, but now I'm going to delay it. So the output will be just x of t minus tau. Now I will make this delayed input to hit the system I am trying to test, which is this one. So the output will be what? Exactly the input multiplied by a factor of 3. So it will be 3x of t minus tau, whatever is the input here. So now when I compare these two, they are the same. So the system is time invariant. All right, let's see this one. Is it time varying or time invariant? So let's take the input here and it goes to the system. So according to these equations, it will take the input and multiply it by t. So that will be t x of t. And just to help you visualize, just imagine if the input x of t is something just like this. Then the output here, it's that x of t, which is this pulse, multiplied by t, so it's gonna look something like this. And now I take this input to a delay by tau. So graphically, the output will be just exactly this delayed by tau. So that's that. And it is just t minus tau, x of t minus tau. So delay, wherever you see t, you just delay it by tau. Okay, now let's take the input x of t goes first to a delay, then to the system. So the system will see the same input, but a delayed version. So now I take the same input, but first to a delay by tau. So now this will be just x of t minus tau. Graphically, if I express this with a pulse, then this will be just a pulse here. Here this tau, this actually will be tau plus 1. Now I will take this input to the system. So what does this system will do? Will take the input and amplify it by t. So the output will be t x of t minus tau. So if you plot this is 1. So the input at this instant of time is 1. So the system will amplify it by time, which is tau. And it's gonna look like this. And this one here, tau plus 1. Now, if you compare this equation to this equation, they don't equal. Same thing, if I compare this plot to this plot, they are not the same. So the system is time varying. So basically the system response will depend on time. And that's how we test if a system time invariant or time varying. Okay, the third classification is instantaneous and dynamic system. When we say dynamic system, that means the system basically has memory, or the output of the system will depend on the present input and past input. So the system will process the current input and some old inputs and give you output. Then we say the system is dynamic. And we say the system has memory because it stores old input. So when a new input comes, it will process them all together. When we say instantaneous system, that means the output at this instant of time depend only of the input at that instant of time. And that means the system has no memory, or we call it also memoryless system. So if I have these two systems, this first system is just an amplifier. So the output will, at any instant of time, will depend on the input at that instant of time, time 3. So this is instantaneous system. Now, if I have this system, now that's a different story. Why? Because now the system depends on the present input and a previous input. So if I want to know what is the system at t equal 5, it will equal the system, the input at t equal 5 plus the input at t equal 4. So the output will depend on the current input and the previous input 1 unit earlier. Then this system is dynamic system. Okay, causal and non-causal system. We say a system is causal if the output at any instant of time depend on the input at that instant of time or earlier input. So that means the output at this instant of time t0 will depend on the input during this time at t0 or earlier. Then we say the system is causal, or basically that means the output of the system was caused by the input of the system, then we say this system is causal. So for example, if I have this system and this is 2 o'clock in the afternoon and an input hit the system. If you see an output at 2 and after, then the system is causal. Why? Because this output, doesn't matter how the output looks, may look something like this. It started at 2 when the input hit the system, or it may start later after 2. That's fine. So maybe the system has some delay, but it's causal. But if the system see an input at 2 and it's giving you an output at 1, then the system is non-causal. And in real life, we cannot build it. So that is the condition for causal system. The output at any time instant t0 depend only on the input x of t at t equal t0 or less. That means at the present input or previous input. So let's take these two examples. And system A, this one, we want to know, is it causal or non-causal? Best way to solve this is you just plot it. So if I have an input x of t, and let me say that input equal, just simple, I can choose anything, 1, 1. Then the output, according to these equations, is 3x of t. So I amplify x of t by a factor of 3, so that is 3, plus x of t minus 2. So that is shifted 2 units, so that is here. So that's y of t. See, when I compare the input to the output, the input hit the system at t equals 0. Your output happened at t equals 0. It didn't start earlier. Then this system is causal. But let's try this system. For the same, let's just assume this is our input. So this is part A. Now let's do part B. It's again the input amplified by a factor of 3. So that is this. And x of t plus 2. That means shift these 2 units to the left. Now that's y of t. Now this system is non-causal. Why? The input hit the system at t equals 0. But the system is already giving you an output 2 units earlier. Before even the input hit the system, it starts already giving you an output, as if it's predicting the input will look like this. Then that's a non-causal system. If that 0 means noon, 12 noon, the input hit the system at 12 noon, but the system already giving you an output 2 hours earlier at 10 o'clock in the morning, then this is a non-causal system. So basically, causal means the output come after the input. Analog and digital system. If the input is an analog signal like this one and the output is just analog, that means the amplitude has many possible values and the time is continuous. And the output is analog, then the system is analog system. Now digital system, that means the system is discrete in time. And in real life, most signal is analog signal. So we first take it to continuous to discrete converter or analog to digital converter. This one is not digital because the amplitude may have many possible values. So we call it discrete. So from continuous to discrete, I just took sample of this one and I got this one. Now I have this discrete time system will process this signal and give you a discrete output. Now, if I want to convert it to analog output that I can hear or see, then I take it to this converter, which will convert discrete to continuous, and I get this signal. And we will learn about digital to analog or discrete to continuous converter. Basically, from these, if I enlarge these, from these samples and maybe previous sample, I can predict what's in the middle. So it become continuous. Interpolation. Okay, the next classification is invertible and non-invertible system. Well, if I have this system and I want to determine is it invertible or non-invertible? Well, this system, if I give it this input x of t and it give me this output y of t, now if I can build a system that will take this output and give me back the input, then this is invertible system. Basically, if I have a system and I can build a system that will do the inverse of it, the inverse operation, then the system is invertible. And if this system gives me y of t and I cannot build the system to recover x of t from here and get this one, then we call this system non-invertible. And we can think in communication, if you have an antenna that transmits a signal, this signal as it travels, unfortunately, it will be corrupted by noise. So now we call this medium where the signal traveled, could be coaxial cable, could be air, a system or channel system. Now at the receiver here, antenna, when the signal arrives, we want to build a system that will inverse the impact of these, basically eliminate this noise and recover back the signal. Well, sometimes if this system is invertible, the type of noise, we can build a system here that will do the inverse of this one or close enough. So then we recover at the receiver the original signal without noise. And that's why we sometimes classify invertible, non-invertible. That's one application. So let's take these two examples. Y of t equal x squared. Is it invertible? If I do this one, this is the system. If the input is 3, the output will be 3 squared. So that's 9. What about if the input is minus 3? Then the output will be minus 3 squared, and that's 9. Now there is a problem. If my output is 9, I cannot build a system that will do the inverse because I don't know if it's a 3 or if it's a minus 3. So this system is non-invertible. It doesn't map the input x to the output y 1 to 1. In this case, two inputs are mapped to the same output, the 3 and the minus 3. So it's non-invertible. Now, how about this system? So this system just amplifier by a factor of 2. So if I have 3, then the output is 6. If I have 5, the output will be 10. If I have minus 3, the output will be minus 6. So it maps each single input to a unique output. So this system is invertible. And what is the inverse of this system? Is it just a 10-weighter? I just take the output and I amplify it by half. All right, the final classification is stability. And here we will just learn the external stability. Later on, we will learn about the internal stability. External stability or bounded input, bounded output. Basically, if I have a system and if I give it a bounded input, that means an input that doesn't go to infinity, and it gives me an output that doesn't go to infinity, then we call it bounded input, bounded output system. We will come back to stability in more detail when we'll learn more the internal component of a system. Then we will classify it as external stability, internal asymptotic stability, and all these. Okay, the next topic is system modeling. And basically that means if I have a system here and it has an input x of t and an output y of t, can I describe the system mathematically such that it will relate the input to the output? So if I have a mathematical equations, something in terms of x of t, I can solve these equations for any kind of input. I can predict or solve it to find the output. And that's what we mean by system modeling. Just find a differential equation or any equation that relate the output to the input. We will learn more about system modeling, and the more complex the system, the differential equation will be of a higher order, 5th order, 7th, 8th, depending on the complexity of the system. So let's just take an example of electrical system and the mechanical system, and we can also do the biological system, financial system, any system. You can describe it by mathematical equations or differential equations. So let's take some examples that you learned in circuit theory courses, but now we're going to look at them from signal and system point of view. So let's start reviewing some of the electrical system component you learned in circuit theory. So the first one is the component resistor. And with Ohm's law, it says the output voltage across the resistor equal the current through the resistor time R, the resistance. If you have a capacitor component, the current through the capacitor equal the capacitance times the derivative of the voltage across the capacitor. And if you have here inductor, then the voltage across the inductor will be the inductance times the derivative of the current through the inductor. And the sign is very important here. See here in this equation, all the sign here positive, positive for this direction of current. So if in the capacitor case, this is true if the current is flowing to the positive terminal of the capacitor. So like this is now in a charging mode. Same thing. This is positive only if the current going through the inductor by passing from positive to negative. If the direction of the current here or here is reversed, then you introduce a negative sign here and a negative sign here. Okay, so this is the electrical system. Let's look at the mechanical system. In a mechanical system, you have a mass, and the input can be x of t, which is a force pushing this mass. Then a displacement will happen, which is y of t. So now the relationship between x of t, the input, and the output y of t is this one. X of t, the force, equal mass time acceleration. And acceleration is just the second derivative of displacement, which is this. These two dots mean second derivative. Now for the spring, if there is a force x of t pulling the spring, then there is a displacement y of t. The spring will be longer. And k is the stiffness of the spring. So then the relationship between the force and displacement, x of t, which is the force, equal the spring constant or stiffness constant time the displacement of the spring. Again, if the force is this way, then that's compression and negative sign here. The third component is the dash pot. And if this is the force x of t pulling it this direction and displacement in this direction y of t, then the force equal b, which is the damping coefficient of the dash pot, time velocity. Velocity in this case is just the derivative of displacement. If you look in the car, behind the wheel of your car, you will find B, the suspension system. It consists of a spring and the dash pot. So these are the components. Just to demonstrate how we model system, we will be using this simple component in the mechanical system or in the electrical system. And then we will see if we can derive the differential equation that describe the input and the output. So let's take an examples. First with electrical system. So we have here a simple circuit. We define x of t as the voltage source, and the output that I'm interested in is the current y of t in this loop. I could choose the output that I'm interested in a different problem, the voltage across the capacitor. I could have chosen y of t to be this one, or the voltage across the resistor. But in this example, we chose our output that I'm interested in, this current. So now I need to model this system. That means I need an equation that will relate the input x of t to the output y of t in terms of the parameters of the system. In this case, inductor, resistor, capacitor. So one way to solve it is just use Ohm's KVL, Kirchhoff voltage law. So if we write KVL going this direction, I'm going from minus to plus, so that's minus x of t, plus the voltage across the inductor, so let's make it plus VL, plus the voltage across the resistor, VR, plus the voltage across the capacitor, VC, equals 0. That's KVL. So I can rewrite this one as VL plus VR plus VC equal x of t. Now, good, I have an equation, and I have the input x of t, but I don't have y of t. That's what I'm interested in. My output is y of t, is the current through all these components. So that means I have to express each one of these in terms of either x and y or just y. So I'm going to be using what we learned about the voltage across the inductor. So this is plus minus, this is plus minus, this is plus minus. And that's how we wrote these. So now the current across this inductor is Y, and the voltage across inductor VL is just L time the derivative of the current. So that is dy dt, because the current I label it as Y. Plus the voltage across the capacitor for Ohm's law is just the resistor times the current, which is Y. Plus the voltage across the capacitor is 1 over C times the integral of the current through the capacitor. So that's 1 over C, the integral of y of t d of t equal x of t. Now I have one equation, differential integral equations, that relate the input x of t to the output y of t. If I'm not happy with the integral, I can take a second derivative of every component just to get rid of the integration, because derivative is the inverse of integration. So if I do this will be L d squared y of t plus R dy of t dt plus 1 over C y of t plus dx of t. And I can use this symbol, and that's in the remaining chapter we will express derivative by d and the second derivative by d squared. Then in this case this will be just L second derivative of y plus R first derivative of y plus 1 over C y equal first derivative of x. I'm dropping x of t, y of t. And I can divide everything by L. So this will be just d squared y plus R over L dy plus 1 over LC plus 1 over L dx. And that is the differential equation that describes the system. It relates the output to the input. So now if I have an input that is a sinusoidal or input that is exponential, I can solve this equation and find what is the output y of t. And in next chapter, we're going to learn how do we solve these equations in the time domain when it's a simple equation like d squared, second derivative, second order. But as these differential equation and the system become more complex, third, fifth, seventh order, we're going to learn how to use the Laplace to solve this equation in the frequency domain. It's much easier. Okay, here I just plug the value of L is 1 Henry, R is 3 ohm, and the capacitor half. So if you're going to plug these values here, that's the equation you will get. And if you take y as a common factor here, later on we will learn this called the characteristic polynomial of the system. We will learn this more in detail in next chapter. Let's now do the same thing for a mechanical system. So you have this simple mechanical system, and I want to find a differential equation or a mathematical equation that relate the output. I chose y of t, my output, as a displacement, and my input x of t, the force. And this is frictionless surface. So since the displacement is in this direction, so it seems like the forces acting on this mass, 3 forces. One is x of t pulling it this way, and the other forces is the spring pulling it this way, and the dash pot pulling it this way. And since the displacement is in this way, it seems the force is winning. So then the equation will be x of t minus the force of the spring minus the force of the dash pot equal be mass time acceleration. Well, good, I got the equation, but I don't have y of t. I am interested on a differential equation that relate the input to y of t. So I have to express this somehow in terms of x or y. Well, let's do that. So x of t stay the same minus. Now the force of the spring we learn is the spring constant k times the displacement, which is in this case y of t. The force of the dash pot is the damping coefficient b times the velocity, which is the derivative of displacement, equal the mass. Acceleration is the second derivative of displacement, so that would be y of t, second derivative like this. And if I express it such that all y in one side and x in one side, then I will take this to this side. So this will be x of t equal mass second derivative of t plus this, or let's do this one first, plus by of t first derivative plus k y of t. I can rewrite this as mass second derivative, that will be d square y, plus b first derivative, that's dy plus ky equal x. And if I want this second derivative has a factor of 1 here, a multiple of 1, I divide everything by m. So this will be d square y plus b over m dy plus k over m y equal 1 over m x. If you look at this differential equation, if I plug value for damping coefficient, mass, spring constant, then this equation will look at differential equation exactly the same as this. If I plug values for resistor inductors. And from mathematical point of view, you have a second order differential equations, the solution will be the same. But in this case, you are finding displacement for a mechanical system. In this case, you are finding the current for electrical system. So from here, the remaining chapters, we will be dealing with differential equation and how do we solve it. That differential equation can be describing mechanical system, electrical system, biological system, financial system, any kind of system. And the solution will be the same for all these types of systems, but the interpretation of the solution will be different depending on the system. In this case, y of t is displacement. Here, y of t is current. In biological system, y of t could be the flow of sodium into the cell wall. Well, these end chapter 1, and next videos we will start chapter 2, which is solving this differential equation in the time domain. Thank you very much and see you soon.